In this video, I'm going to calculate the position away from the planet where the force of gravity is balanced in the two directions towards the sun and the planet, or for the case of the Earth and Moon, the force towards the Earth and the force towards the Moon, where the position where those two forces balance. So the net gravitational force would be zero. This calculation is going to ignore orbital motion. That is important for deciding if some planet is going to retain a moon or not. I'll have some comments on that at the end of the video. The video is going to do the cases of the Earth and the Moon, the gravity balance point between the Earth and the Sun, between Mars and the Sun, and between Jupiter and the Sun. So let's start talking about how this calculation is going to be performed. So we have some small mass that we're going to put in between, for example, the Sun and the Earth, and decide where, we're going to calculate where, the force of gravity on that mass is the same magnitude, but in opposite directions. So, for example, towards the Sun and towards the Earth. I'm going to label these masses M1 and M2. M1 is going to be the larger mass. For example, M1 would be the Sun, M2 would be the Earth. Or for the case of the Earth and the Moon, M1 would be the Earth and M2 would be the Moon. And we can write a mathematical description of where the at the time these two forces are balanced. So I'm kind of writing in between my drawing here, but M1, for example, the Sun, and M2 out here, the Earth, and the small m, some very small mass that's in between the Earth and the Sun. There's going to be gravitational force of the Earth on this object that would tend to draw the object towards the Earth. And there's going to be gravitational force of the Sun on the object that's going to tend to draw the object towards the Sun. So the magnitude of these two forces balance. That's the point that we're interested in. There's a distance r from the center of the Sun to the center of the Earth, for example. We'll use a symbol r for that. X is going to be the distance from the center of the small object to the location where the two gravitational forces balance. So the gravitational force, let's say this is the Sun, capital G, M1 would be the mass of the Sun, small m is the mass at this balance point, and then divide by the distance from the center of the Sun to this small mass. R is the total distance between M1 and M2. I have to subtract off X to get the distance just from this balance point back to the Sun. Then that has to be squared. GMM divided by R squared. For the force of attraction on this small mass from the Earth, for example, on the right, capital G, mass of the Earth, mass of the small object, and divide by X squared. So this is the calculation that we're going to have to perform. We're going to have to find the value of X. So I'm not going to do every step here, but if I would cross multiply, I get M1, the large mass, times X squared equals M2, and I've gone ahead and squared the parentheses here. So R squared minus 2RX plus X squared. And then we can gather like terms. If I divide both sides by M2, I'd have M1 over M2 times X squared here. I have an 1x squared here that I'm going to subtract from both sides. So it leaves me with a coefficient M1 over M2 minus 1 times the x squared. The 2rx, I add that to both sides. The r squared I subtract from both sides equals 0. I've got a quadratic equation, and we have numbers for the masses, for example, of the Sun and the Earth. We know the distance from the Sun to the Earth. This x is our unknown that we'll solve for. And again, r is the distance from the Sun to the Earth, or for the other planet situations. So this is solvable. It's quadratic. There are two solutions, and you have to use the value of x that's positive in the solution. So we want to find that x, and that will give us the place where the gravitational forces balance. And then we can talk about using this information and talk about whether this planet can have a moon. If we can make some comments about the ability of the planet to retain a moon. So you might want to pause the video and write this expression down and solve it once with your calculator. Look up the masses that are involved for the Sun to the Earth and Sun and Earth, and the distance from the Sun to the Earth, so you know the value of R, and plug that in. And here are the results that I have for the situation of the Earth and the Moon first. We'll draw this down a little bit so it's not so much glare. But for the Earth to the Moon, the balance point is 3.61 times 10 to the 7th meters from the Moon to this balance point. Doing the Sun and the Earth, 2.54 times 10 to the 8th meters from the center of the Earth to this balance point. For the Sun and Mars, 1.17 times 10 to the 8th meters from the center of Mars to the balance point. And for the Sun and Jupiter, 2.22 times 10 to the 10th meters from the center of Jupiter out to the balance point. Now, here are some facts, orbits of that happen to take place. Our moon has an average orbit size 3.84 times 10 to the 8th meters from the center of the Earth. Notice this is larger, quite a bit larger, than the where the balance point is located. So that might give you a little pause here. How can this this object be so far away from this balance point? Isn't it too close, too far away from the Earth's control? I'll get to that in just a minute. Deimos, orbiting Mars, 2.35 times 10 to the 7th meters away from the center of Mars. And it is inside this balance point distance. So Mars is completely able to control the motion of Deimos. Deimos orbits Mars close compared to where this balance point is of gravity between the Sun and the object and Mars and the object. And then for Jupiter, its outermost Galilean satellite is Callisto. It has an orbit size of 1.88 times 10 to the 9th meters. That again is fully inside the region of space where Jupiter's gravity dominates over the gravitational force of the Sun. If this was 3 times 10 to the 10th, that would put Callisto more in the range of where the Sun's gravity exceeds the force of the Sun's gravity on the object would exceed the force of Jupiter's gravity on the object. However, there are satellites of Jupiter that are further away from Jupiter than this 2 times 10 to the 10th meters. So how can that be? Well, this calculation here involves just a static situation, just a calculation of the position where the forces of gravity balance. I'd encourage you to read up on what's called the Hill sphere. In Wikipedia, there's a readable article regarding the Hill sphere. And when we have the objects moving in an orbit, for example, the Earth and the Moon going around the Sun, this region where the Earth can control the stability of the orbit of the, for example, the Moon, it's larger. It's larger than this balance point here, the object does not have to be inside 3.61 times 10 to the 7th meters away. So we have a situation for what's called the Hill sphere, where the moon can be further away from the planet than you might think. And what's happening here is that the planet, let's talk about the Earth and the moon. The Earth is influencing the motion of the moon such that it kind of goes back and forth around in the orbit. The moon actually is orbiting the sun. The moon does not orbit the Earth. The moon orbits the sun, and the Earth just pulls it back and forth. It's going to be a very crude drawing here. So the sun at the center, and the Earth going around in its orbit. As the moon goes around in its orbit, this is not to scale, but the Earth is kind of whipping the moon back and forth across the orbit position of the Earth. And the same thing happens to the Earth, but in much less distance. The Earth is getting pulled back and forth by the moon as well. But the Hill sphere for the Sun and the Earth situation is 1.5 times 10 to the 9th meters. The moon is inside, the moon's distance from the Earth is inside this Hill sphere distance. So the Earth is able to control the motion of the moon, even though the moon experiences more force from the sun than it does from the Earth. The sun is the major controlling factor in the motion of the moon in space. The Earth just kind of perturbs the motion of the moon back and forth across the Earth orbit situation. So a few facts there about gravitational balance position, these numbers of x that I've calculated, and a comment on our moon is the strange one in this group. Our moon is further away from the planet, outside of the strict gravitational control of the Earth. Deimos and Callisto, they're fully inside the gravitational influences of their host planet. So hope that's interesting, perhaps useful, perhaps not. You might search for some other physics and astronomy videos. They're listed on my websites. These websites totally free, no registration. You do not give me your name. You do not give me your email address. I just list the videos here so they're more easily found on YouTube. Ask your instructor if you have a few questions here about gravitational balance and orbits of objects.